We are now focusing on the constraints. So we forget about the objective function for a while, and we look at the constraint set. And first, we will assume that the set of constraints is linear, meaning it's defined by linear or affine functions. And actually, in this case, the geometrical object that characterizes the constraints is called a polyhedron. A polyhedron is defined as the intersection of half spaces. So basically, it's a set of linear inequalities. The formal way to write the polyhedron is by saying that it's the set of x in Rn, verifying a linear inequality ax less or equal to b, where A is a matrix of m lines and n columns, and B is a vector of m entries. So here, this polyhedron is defined by the intersection of m half spaces. So this is an example of a polyhedron in 3D. Okay, so this is the type of objects that we will be dealing with. The polyhedron P, defined as I just did, is a convex set. So what is a convex set? A convex set is a set, let's call it here X, such that when you take any two elements of the set, X and Y, the line section that joins the two elements also belong to the set. So an example of a non-convex set would be something like this. In this case, if you take X here and Y here, the line section that joins the two does not completely belong to the set. So the second set is not convex. In the case of a polyhedron, we have a convex set. The formal way to write the convex property is to say that for all lambda between 0 and 1, the convex combination of x and y defined by lambda, meaning lambda x plus 1 minus lambda y, belongs to P. So you can check that when lambda equals 0, this is equal to y, this expression, and when lambda is equal to 1, the expression is equal to x. And for each value of lambda strictly between 0 and 1, it corresponds to a point on this line between x and y. And the condition is that all these points must belong to the set if it is convex. Okay, so we have a convex set. Now there are various ways to represent a polyhedron. The first way is called a canonical form, and this is the form that I used in the definition. So canonical form would be the set of x in Rn such that Ax less or equal to b, where A is a matrix of m rows and n columns, and B is a vector of Rm. Another way to represent a polyhedron is called the standard form. So the representation in standard form is the following, is the set of x in Rn such that A times x equal b and x is non-negative. Okay, so these are two possible representations of a polyhedron. And actually, the canonical form will be most helpful to derive some geometrical intuition about the polyhedron, while the standard form will be helpful to do some linear algebra manipulation of the polyhedron. So it is actually possible to transform one representation into another one. So if you have here the canonical form of the polyhedron, which is characterized by a set of inequalities, we can write it as a set of equalities that is required by the standard form by including the so-called slack variables. If you remember, we have already seen this when it was about transforming an optimization problem into another one. Slack variables allow to transform inequality constraints into equality constraints. So when we include the slack variable, the inequality constraints become ax plus xs equals b, and xs is non-negative. So the slack variable basically captures the distance between the AX and the B. And this distance must be positive so that the inequality is verified. The polyhedron can now be represented as the set of X in Rn and the set of XS in Rm, such that AX plus XS equal B and XS is non-negative. So it's interesting to note that by transforming the canonical form into a standard form, the dimension of the polyhedron changes. In canonical form, we had a polyhedron in Rn. N was the number of variables. But now we have included the slack variables. So because we have included the slack variables, the total number of variables involved in the polyhedron in standard form is n plus m. N, the number of original variables, m, the number of slack variables, one for each constraint. Now let's look at a specific constraint. Let's take the constraint number j. So constraint number j is written as aj transpose times x less or equal to bj. Okay, so aj is the row number j of the matrix A, and bj is the component number j of the vector b. So this is the constraint, one of the m constraints of this polyhedron in canonical form. What we do is when we include the slack variable, we write the constraint like this. So now we have aj transpose x plus the slack variable xjs must be equal to bj, and the slack variable must be non-negative. Now let's look at what happens when the constraints are active. An inequality constraint is active when it is verified with equality. Okay? So when it is verified with equality, the less or equal here is replaced by equality. Then it means that the constraint is active. So what would it mean in the context of the standard form of a polyhedron? Well, it means that this inequality here is replaced by inequality. So it means that an active constraint in the polyhedron of canonical form is equivalent to a slack variable being equal to 0 in the polyhedron in standard form. And we will use this equivalence when we will do some geometrical interpretation of the optimization problems. We will draw the polyhedron in canonical form because it's easier to represent, but we'll have to interpret it in the context of a standard form because it's easier to manipulate in algebraic terms. And so when we will see an active constraint in canonical form, it will be equivalent to a 0 slack variable in the standard form. So in this video, we have introduced the concept of polyhedron, which is the intersection of several half spaces in Rn. And why? Because a polyhedron is actually characterizing the set of constraints of a linear optimization problems. And we have seen two forms, a canonical form, which is actually corresponding to the definition of intersection of half spaces, and a standard form that will actually be more convenient for linear algebra manipulations.